Okay, thank you. Okay, so let's begin. Hello, everyone. I'm delighted to be here to share the results of our research on neuron residual radiance field for streamably and free viewpoint videos. And this project would have been possible without the dedication and hard work of my colleagues and collaborators. Okay, so let's get right into it. Neural Radiance Field has demonstrated remarkable capability to in the task of novel view synthesis, enabling photorealistic image rendering. So NeRF's success has inspired many attempts at dynamic scenes, enabling free viewpoint videos. Yeah. So, however, using existing NeRF techniques for real-world scenarios posed significant challenges. So current neural rendering techniques for preview videos are limited to offline rendering and require extensive storage. This means users cannot interact with the viewpoints in real time, and the distributing such large data is a challenge. So in our work, we aim to make the viewing free viewpoint videos as simple as streaming regular 2D videos. So here is the demo video. As demonstrated in this video, our approach called ReRF, the Neural Residual Radiance Field, allows real-time streaming of FVV data and user interactions. To achieve this, we have developed a novel representation and associated encoding decoding algorithm. Before we dive into ReRF, let's briefly review the original NeRF. Given calibrated multi-view images as input, NeRF can construct the geometry and appearance of a scene or an object. To render pixels in the target images, ReRF casts the camera rays through the optical center and the pixel into the space. And it will also sample points along the rays and use a multivariate perceptron to predict RGB color and density values for each sample point. Volume rendering is then applied to accumulate weighted color based on densities for that pixel. And the entire pipeline is differentiable, so it allowed end-to-end supervision from captured images. So that's the cool things for NeRF. So other hybrid methods offers much faster rendering speed, but require more storage. So inspired by the DVGO method, our ReRF leverages a voxel-grid representation, enabling faster rendering with significant smaller storage requirements for similar rendering quality. So as shown in this table. So how does it work? So let's look into a simple toroid example. Assume we have trained a feature grid using DVGO, where each vertex in the grid stored a feature vector. We then partitioned the grid into A times A times A voxel groups, each of which can be reshaped into a load vector. These load vectors are arranged into a matrix. Applying singular value decomposition SVD to this matrix for low rank approximation shows a smaller impact in the rendered results. So which means that even once we have the reconstructed feature grid and do novel view synthesis using this reconstructed feature grid, we can get a very also high quality rendering result. We observed similar results in multi-frame cases. So this suggests that there must be some information redundancy in the feature grids. Based on these insights, we employ a compression method based on 3D discrete cosine transformation DCT, also called DCT. The details of these algorithms are quite complex, so here I just give you a rough overview of the process. The process involves transforming voxels into the frequency domain, and then we quantize the DCT coefficients. And finally, we will perform the entropy encodings to obtain the compressed data. So that's the one way to compress, a very simple way to compress the feature grid. So let's turn into the dynamic scenarios. ReRF employs several strategies during training to enhance the interframe and redundancy and boost the compression rates. So this is the pipeline of Leuven residual radiance field. Firstly, we will utilize motion composition mechanisms, assuming that we have already trained. So we use this so this motion compensation mechanisms use the cost deformation field to warping the feature grid from the previous frame. So and then on top of the warped feature grid, we land a residual grid to do the compensation. And lastly, we use L1 normalizations, regularizations to regularize the residual grid to make the residual grid as sparse as possible. So now let's take a look at our ReRF representation. It consists of the first frame's feature grid from the original DVGO, and then paired it with residual and motion grids from the subsequent frames. We also introduced the concept of the groups of the feature grids, which enables rapid seeking during video playback, enhancing the user's experience. So these figures demonstrate an overview of our proposed ReRF-based codecs and the players. So let's take a look at the ReRF compression experiment for results in static scenes. Our method achieves the minimal storage requirements while maintains a high PSNR. Note that ReRF offers flexibility to control the amount of storage. You can see the figures on the top right. So we can control the size of the storage, but it will also influence the rendering quality. Let's take a look at the experimental results in dynamic scenes. Even with data which has around 4,000 frames, ReRF consistently maintained high quality outputs. In contrast, other methods exhibit noticeable quality degenerations and are unable to handle ultra-long sequence data directly. So the rate distortion curve on the right demonstrates that motion-aware residual representation significantly enhance the compression rate in dynamic scenarios.